Hi there. Welcome once again to our Smart Mate session. I'm Sito Bejani, and in today's session, we'll be looking at a voltage divider bias circuit. In your screen, our example is extracted from example 3.4 from the TVET First by Macmillan and Troop and Publishers textbook. We will be doing the calculations on this circuit so that it could assist you see the simple steps that you could apply. Here, the question reads as follows. Consider the circuit in figure 3.9 and draw a DC load line and determine the Q point. Assume that the transistor is a silicon. Now, each time when a question wants you to assume a transistor is a silicon, you must know that VBE, if the transistor is a silicon, VBE will be given as 0.7 for a silicon. Sometimes the examiner may choose not to tell you, just as you see in this example. The examiner may choose not to tell you if this is a silicon or it's a germanium. But if it's a germanium diode, that means your VBE will be equal to 0.3 for a germanium diode. For a germanium diode. Now, they want us to draw our DC load line. How should our DC load line look like? And when they say we must also identify a Q point, how are those things? Now, let us have a structure like this, right? This is what we have. We are going to have the value of IC here. The value of IC will be in milliamperes here. And then we will have the values of VCE here. Of course, it will be in volts. Now, here we need to identify three things. First, we need two things basically. We need to draw the DC load line like that. We need to draw our DC load line just like that. And after drawing our DC load line, we need to then identify our Q point. Let me just assume that we identify our Q point to be here. This being your Q point. If that is your Q point, then it automatically means here you will find the value of VCEQ, Q for Q point. And here you will also find the value of ICQ, right? That means the values here would be the value of IC and the value here would be the value of VCE. That is basically what we will be doing. So we need to identify what the value here is, what the value here is, what the value there is, what the value there is. Right? Perfect. Now, let us start calculating. Step 1. We need to draw our DC load line. So for us to draw our DC load line, we will use the equation VCC is equal to VCE plus IC RC R. Let me do this. Let me say plus. Let me say IE RE. This should be RC. But remember, let me write remember. IE, what's happening here? IE is equal to IC. If IE is equal to IC, that means VCE plus IC into RC RE. Can you see that? Can you see that? Perfect. That is the equation that we'll be using today. Now, because we don't, care much about VCC, let's just, interchange those things. Let's write it in a form: VCE is equal to VCC minus IC into RC RE. We include RE because in the circuit we do have RE. Can you see that? We include it that way. Now, the value of VCE here on the y-axis cuts through the y-axis, right? When this graph cuts through the y-axis, it means the x-axis. It means that here our coordinates will have the value of y as equal to 0, right? And what is the value of y? The value of y is IC. I repeat, for our DC load line, we are going to have this. It's like a straight line graph, basically. It is like a straight line graph. So we'll have this graph cutting through the y-axis and the x-axis. What do we know about the coordinates on the x-axis for x-intercepts? We know that for x-intercept, y will be equal to 0, whilst the value of x is maintained. And in this case, the value of x here will then find the value of x here, but the value of y would be definitely 0. It means that here we'll be having VCC minus 0 multiplied by RC RE. That is our VCE. Automatically, this will be 0. So your VCE will be equal to VCC, which according to this, our VCC is 20 volts. Did you see that? It means that the coordinate here is 20 volts. Now we've found our VCE, right? What is the next thing that we need to do? We need to find our IC here. We need to find our IC here, right? Our IC here, what is happening here at y-intercept? What is the value of x at y-intercept? The value of x at y-intercept is equal to 0. The value of x at y-intercept will be equal to 0. Can you see that? So it means that the value of VCE here will be 0. So if we take our equation just like that and we say this was step 1, now we're looking at step number 2, and we say here VCC is equal to VCC, which is 0 plus IC into RC RE. Then we need to make IE subject of the formula. Therefore, IC will be equal to VCC divided by RC RE. Can you see that? So now we substitute that. VCC is equal to 20 divided by, what is the value of RC? The value of RC is 1.2. Is 1.2 exponent 3 plus RE, it's 2.5 exponent 3. 2.5 exponent 3. What is the answer there when you punch that in our calculators? Remember, you always reset your calculator at all times. This is 1.2 exponent 3, 2.5 exponent 3, just like that. And our answer here for this current will be 5.405. 5.405 milliamperes. Now, this is the value of the current here. It's going to be 5.405 milliamperes. Now, we've already identified the IC and the VCC. VCE. So we need to find ICQ and VCEQ. We need to find ICQ and VCEQ. Can you see that? Perfect. That is perfect. So what is it that we want here at this point? We need to find the value of ICQ. The value of ICQ, the value of ICQ at this point should also be equal to the value of IE. But I can't use this one based on this equation. I need to calculate the new value of IE. I need to calculate the new value of IE. And the new value of IE is calculated by VB minus VBE divided by RE. I have RE, I have VBE, which is said to be a silicon, that is zero point 0.7, but I do not have VB. Now, where can I calculate VB? VB would be given by RB2 over RB2 plus RB1 multiplied by VCC. As the name implies, voltage divider bias. We have two base resistors on the circuit, so we will calculate the voltage drop across that when that type of a voltage is divided. Now, we have 1200. Let me just put it as 1.2 VP2. No, sorry. VP2 in this case is 6 exponent 3, 6 exponent 3 plus 1.2 plus 1.2 exponent 3 multiplied by VCC, which is 20. Now let us punch that in our calculators. We punch that in our calculator. 6 exponent 3, 6 exponent 3 plus 1.2 exponent 3 multiplied by 20. What do we get? We find that the value of VB is 16.667. 16.667 volts. 16.667 volts. We take this one and then we substitute it there. Therefore, our IE is equal to 16.667 minus 0.7 divided by RE, which is 2,500 basically, which is 2,500. So I'm going to say answer 0.7 divided by 2,500, and I find that the value of IE, is it correct? Is it correct? Where did we make a mistake here? That value can't obviously be greater than that one. Yes, I think we made a mistake here. This was supposed to be 12. Let us fix that. This was supposed to be 12 and this was supposed to be 6.667. Just like that. In that case, if we put our, let's go back there, 6.667, just like that, we get 2.387, 2.387 milliamperes. This value of IE, new value of IE, would be equal to the value of ICQ. Can you see that? Would be equal to the value of ICQ, would be equal to the value of ICQ, just like that. Now, we need to take the value of ICQ here and substitute it in this equation right here, and substitute it here and get the value of VCEQ, right? And get the value of VCEQ. Let's just create some space here, there, just a small space, just a small space there, just a small space there. So the third or fourth step here, we will then say VCE, but instead of just leaving it like that, I'm going to put a Q. This indicates to me that now I need to put a Q even on the IC. Would be IVCC, ICQ into RCRE. Can you see that? This is 20, and here we have 2.387 exponent negative 3. Let's put that in our brackets, and then here we will be having 1200 plus 2500, and then we punch that in our calculators. We will get 20 minus 2x 387 exponent negative 3. That's 1200 plus 2200, 500, sorry. This will give us 11.168. 11.168 volts. Now, look at this. We have identified all the values here. You see, ICQ would be 2.387 milliamperes, whilst VCEQ will be 11.168 volts. That is exciting. That is exciting. How many steps did we use here? One, two, three, four. And the fifth step is our drawing. We've identified the IC values there and the VCE values there. We've drawn our DC load line just like that. And then we identify our Q factor. We first Q point. We first calculated our ICQ and then substituted the value of ICQ into that equation. And then we find VCEQ. We put it in just like that. This is a knowledge that you already possess from N4, though we had calculated differently because we did not have beta. That's it for me today, folks. Let's meet again next time for another exciting session of industrial electronics.